have a look. Okay, please get your notebooks out. You need to come forward. That's advisable, but that's up to you. So here's the problem. These won't, for some reason, maybe the file's too big or something, but they won't send to my email here. So I'm just going to draw them. So here's the first one we're going to take a look at. We're on chapter 3. This is the optimization stuff. Chapter 3 is huge. I know. Okay, so we're going to help a farmer out here. A farmer wants to fence a rectangular pasture. Actually, hang on. No, we're not. Yeah, we're helping out a rancher. It's better for Pendleton anyway, huh?
We have a lot of farms.
Only until slaughter.
No, then it's not when FDA. It still matters because we want the food. How deaths matter too. How deaths matter. How everything. Cows matter.
I think you forgot a word, oh yeah.
Yeah, 200
Feet.
feet up to and
Oh, yeah, you need something there, don't you?
cows. 10.
What time?
Are you recording? Excuse me, Shaggy. Are you recording?
I am. Thank you for asking.
So is my voice on record?
Yes, it is.
Yes. I'm gonna go listen to it later just to hear your conversation. I'll show you.
Okay, there we go. So let's kind of start to break this process down into steps. So we looked at an example a couple days ago. What's the first step, probably?
Drawing picture.
Yeah, exactly. Draw a picture and let's define the variables, right?
Right.
Okay, so here are, we got these two rectangular corrals that are adjacent, so it's just going to look something like this, isn't it? Right?
Yep. Yep.
What variables could be used to describe this arrangement?
X and Y.
L and W we could use. I'm going to use X and Y just because they're easier to write, and L looks like a 1 sometimes. So let's call this distance right here X and there, and let's call this distance Y. How about?
Wait, why are they two different? Those are two different areas. Two different pastures for different animals.
Yeah, there's two adjacent corrals. Okay, for I don't know, horse.
Wait, I think they're two.
Okay, that make sense?
Yes.
Okay. So there's step 1. Okay, now step 2. Remember what step 2 is?
Create a formula. Yeah.
Okay, yeah. And what do we call this? Primary equation. Good. Good. So we could call this like step 1, and step 2 is going to be our primary equation, which is always going to be what? What kind of quantity? The quantity that we're trying to optimize, maximize or minimize. So what is that? Area. Okay, so then we need to come up with an equation for area, right? So what's area equal to? Okay, so okay, so 2x times y.
Oh, why 2x? Why not
X, well, because I'm just doing this total distance times that total distance,
Why
right?
was the other one x squared? With the
Well,
box?
because that was a different problem. That was a problem where we were doing a surface area of a box, right? So we had an area on the bottom that was an x squared, had a square base, right? So this is maybe a little easier problem in a way. It's just 2xy. Now notice that a is a function of two variables there, right? X and Y. Okay, so if it wasn't, if our primary equation is right from the beginning a function of one variable, that makes us happy because we don't have to come up with a secondary equation or an equation of constraint. We can just do the math, right? Okay, but here we've got two independent variables, and so that means, what do I have to do about that? Say it again? Well, okay, I'm going to have to come up with a substitution equation. I have to come up with a second equation to relate those two variables, right? Okay? So we need a secondary equation, which we can call an equation of constraint.
So step 3 is equation.
Step 3 is kind of optional sometimes, right? It either do it or you don't based on if you need to, right? In this case, we need to. So step 3 is our equation of constraint. Well, what's the constraint? If there's no constraint, the answer is easy. We'll just make the area infinite. But there must be some number up there constraining us. 200 feet. Okay, 200 feet of fence. So what is that? What's equal to 200 feet here? Okay, so the kind of the whatever is sort of the modified perimeter, right? For the fencing. So what's that going to be?
Perimeter? Oh.
Because all that green stuff has got to be fenced, right? Yeah, 3y plus 4x,
Wait, how are
right?
you getting this? I don't get this.
Okay, how do we get that? Because I've got to do look at all these what we see as being vertical, right? The vertical sides are all length y. So I have to have 3 of those, and I've got 1, 2, 3, 4 sections of length x.
Okay.
I'm just adding up all the fencing based on the little segments that we've developed, right? So our equation of constraint, we get 4x plus 3y equals 200. Okay. Now we've got to isolate a variable in our equation of constraint. But remember that when we isolate a variable here, we want to be smart about this. In some cases, it's not going to make any difference which variable we isolate, but in some cases, it makes a big difference. It did the other day, right?
Yeah.
It was much easier for us to isolate one of the two variables than the other. And there's two things that contribute to that. I'm dealing with a system of two equations, right? I'm going to use the red equation as my substitution equation, but I'm substituting into the black equation, right? Either one of those might provide a compelling reason to pick one variable or the other, right? In this case, it's pretty much even Steven, right? I mean, it's, there's 1x and 1y down here, 1x and 1y up there. They're all to the first power, so it's pretty arbitrary. Why don't we just solve for y? Not that it really makes any difference. Y? So if we solve for y, we're just going to get in the numerator, we'll get our 200 minus 4x and then divided by 3, right? So let's put a box around that because that's our substitution equation. And we'll probably come back to that later, right? So we're going to substitute into our primary equation, and what do we get? So if we do that, we've got A.
Is this step 4 or still 3?
I guess you could probably still call this step 3. Step 3 is come up with a secondary equation and substitute it up. Okay? So we get A equals 2x times that, right? Times y, but that's our substitution. So 2x times the quantity, 200 minus 4x over 3. So what's that equal? And notice now we've got A as a function of one variable, right?
Yeah.
Okay, that's good. Can simplify a little bit though, right? We don't want to use the product rule because we're going to differentiate this. So let's go ahead and distribute the 2x and get what? 400x minus 8x squared, and that's all over 3. just pull the 1/3 out front if I want to. Okay? So there's my start of calculus, really. Right? Now we're to the point where we have like an f of x, only ours is a of x. Right? What else do we need here, though? Think back to all the stuff we did with the tables. We did tons of stuff like this. Where did we always start before we did calculus? Domain. Right, we need a domain. So are there any restrictions on the domain
No.
mathematically?
No.
No, the math gods say no problem, right? But
Yeah.
this is a real world problem, and so we have to look at this from the perspective of a real world domain. We have some finite amount of fencing. Well, what's the smallest that x could be? I mean, what's sort of the lower limit?
1.
Well, I could make x 0.1 if I wanted to. 0, right, okay, so 0 really wouldn't make any sense, but any value greater than 0 is possible. We can probably see that a really tiny value like 0.0001 is not very practical, right? But really our domain is just going to be restricted to all the values of x that are greater than 0, right? Okay, so what about the upper end? Let's look at this. Now, this is a little bit tricky. I want you to think about this. The upper end, what's the upper end value of x? As x gets really big, well, how big could x be here? Think about this. In our picture, x and y are inversely related, aren't they?
Yes.
Okay, and this takes a little bit of thinking. I want you to think about this like a cartoon for a second. Would you agree that if I stretch this thing out this way, it's going to collapse that way a little bit?
Yes.
Because the total perimeter has to be, total amount of fencing is fixed. It's 200, right?
Yeah.
So x gets small, y gets big, right? Y gets small, x gets big. Okay, what's the smallest that y could be?
2.
I mean, it could be 0, right? If it went to 0, well, I mean, really, we could even let x equal 0. It just doesn't make any sense for us, right? What if y went to 0? If y went to 0, then this equation right here tells us what would happen to x. I could use really either one of these things, right? Maybe it's even easier to use this guy right here. If y goes to 0, that term disappears. What value would x take?
Big 1.
Well, no, it'd just be 50, wouldn't it? 4x equals 200. So the upper limit for x would be 50, really, wouldn't it?
Yes.
Right? It's got to be somewhere between 0 and 50. X can't be more than that because that would require more fencing than we have, right?
Wait, but look at this too. Have 200.
I mean, that might be kind of a dumb thing to do because if we let x be 50, then y would go to 0, and what's going to happen to my area? It goes to 0, so that's not a very good idea. We're trying to maximize area, right?
Yeah.
Does that make sense? So our domain is going to be 0 to 50.
I don't get how you figured that out. How would you?
So let's look at that again. So we're just going to ask ourselves, what's the smallest that x could be? Well, when x is small, y is big, right? Okay, that's fine. If x shrinks way down, y is going to get bigger. X could approach 0. It could even be 0. I mean, we could include 0, but we know that's not going to work, right? That's going to give us 0 area, so why include it? We could. Okay, so what if we went the other way? Instead of making x small, what if we made x big? Well, if we make x big, then y is going to shrink, right? We can't make x infinitely big because we are constrained. We're constrained by this equation right here. The sum of 4x plus 3y is equal to 200. So the biggest we could get would be if y went all the way to 0, right? Because y can't be negative, agreed? It makes no sense. So if y goes all the way to 0, then our equation of constraint would just become 4x equals 200. So if we just solve for x, what do we get? 50, right? So the biggest x could be is when y gets to 0, and that would be 50. Okay?
Yeah.
So there's our domain, right? It's good for us to find the domain because now we only have to look for critical numbers on this domain. If we get a critical number outside the domain, which can happen mathematically, we just don't worry about it, right? That's work we don't need to do. Okay, so we're squarely in calculus mode now. What do we do with the calculus?
Find the derivative.
Okay, we find a derivative. So here's our function, right? We're going to take the first derivative, and
So step
what do we get? The one. Now, what about that 3 on the bottom? Is that important, really? I mean, what is that?
That's constant.
It's a constant that's really a 1/3 out front, almost, right? Okay, so we don't really have to worry about that. We're just differentiating the parts that have x on the top. What are we going to get? 400.
minus 16.
400 minus 16x over 3, right? Okay, so let's ask ourselves then, when does this equal 0? This equals 0 when what?
400 divided by 16.
Yeah, okay, when the top equals 0, right? Which would be when 16x equals 400. Everybody good with that? Okay.
Wait, why? I get the top part. Why is it?
Well, because I could write this just a 1/3 out front. It's just a constant, right? Just leave it out front. Okay. Okay, so if we divide both sides there, we're gonna get what, 25? Isn't that right?
That's a really big number.
Yeah, that's right.
16 times 25 is common.
I think, yeah, that's right.
Yeah, that's
Yeah.
so right, actually.
It's so right. It's not just right. Okay, so x is 25, right? There's our one critical number. But now let's think about this in terms of the table, right?
Yes.
So how about if we'll make this a small table down here, I guess.
We don't need to find the second derivative.
Okay, does that make sense for our table? We've got our independent variable, it's like the x-axis, and then we got the 3 rows corresponding to function, first derivative, second derivative. Real quick, let's review just kind of our understanding of the structure in this. The first row, these are just y values, right? It's all they're good for. All these are good for is to create ordered pairs so we can orient ourselves or find specific places on our sketch, right? That's it. Nothing else. Second row, this is the first derivative row, so this is the row that has to do with whether the function is increasing or decreasing, right? And this is where our first derivative critical numbers will show up, right? And then the last row, the a double prime row, the second derivative, that has to do with concavity. And that's where the second derivative test will show up, right? In general, we want to work as far down the table as we conveniently can. Is it convenient to take a second derivative here?
Yes.
Very much. So we should take a second derivative.
Let's take.
Okay, so our second derivative equals what?
Negative 16.
-16/3. So it's constant and negative. It's negative everywhere, right? So now let's fill in the blanks on our table. Our domain goes from 0 up to 50. We got one critical number at 25. So what do I do to my table then, right? Those are the important x values. What do we do?
That's
Well, okay, maybe. Let's just work our way down. We don't, it never asks us for the area, does it, in this problem? I think it just wanted to know what are the dimensions, right? So we don't really need to know that value. If it did ask us for area, if we found out that this was a maximum, we might want to fill in that spot, right? Because that's the answer to our problem. But it doesn't, so we don't even care. We don't even need this second row. It's, right? We won't do anything there. What about the third row? Does anything go there? Yes. I've got a 0 because I had a 0 of my first derivative at that critical number. Okay, if we were using the first derivative test, I would just pick a test point here and a test point there and find the signs of the first derivative, right? To determine what kind of thing this was. Minimum, maximum, or neither, right?
Yeah.
Okay, but we
it's
would,
always negative, isn't it? Because
but we're not gonna do that because the second derivative was so easy to take, right? The second derivative gave us a negative value, and so this tells us everything we need to know right there, doesn't it? Right? Think what this means. The middle row, or excuse me, the a prime row is telling us derivative equals 0. What's that mean?
maximum.
Well, no, that doesn't mean maximum, it just means what about the tangent line?
It's zero.
It's flat, it's horizontal, right? That's all that's telling us. This is just telling us that, right? What does this part down here tell us? Yeah, okay, that's telling us that it's concave down, which makes it a maximum, right? Make sense?
Yeah.
So it's a relative maximum. Now, I want you to do the logic here for me. You gotta think about this. We're supposed to find the dimensions that maximize area. How many critical numbers are there in our domain?
One.
One. So how many possible extrema are there?
One.
One. We already know, and we could do this if we wanted to. We would know that at this value, the area would be 0, and at that value, the area would be 0, right? So what's the value of x that's going to maximize area?
25.
25. There's no other possibility, right? If you're thinking, well, how do we know? Maybe this thing could have turned and gone up again. It can't, because that would have required another critical number, right? There's only one.
So, what does that 25 say? What does that mean?
So that tells me the value of x in our picture that's going to maximize area.
Okay.
How about this one? Did we even need to do the calculus?
No.
How come? Somebody defend that. Well, we probably could have just, we could have really finessed our way through this and said, we don't even need the calculus, really. Because we know that if we had, for example, included these endpoints, which we could have, the values of A would have been 0 at both of those, right? Okay. Would you agree that we could easily accept that there's got to be some value of x between 0 and 50 that has some area,
Yeah.
right?
Well,
Does that make sense?
parabola, we just don't get that. We know that in the middle of it, would have been the highest point.
Well, we wouldn't know that's necessarily the middle. Well, actually, yeah, we would have, because it is quadratic. You're right, we could have. I guess we need to do a little calculus. I guess we would have had to do enough calculus to find that critical number, but we didn't really need any tests to show that that's a maximum, right?
Just a baseline.
Because we know, don't we know that there can only be one extremum in this whole thing,
Yeah.
right? And so that's got to be it, right?
And we know that because there's only one.
There's only one critical number, and the value is 0 at both endpoints, and so it's got to be a maximum. We don't even really need the second derivative test there. It's so easy to do. That's probably the easiest way to show to defend it as a maximum. Does that make sense?
Is that 25 feet?
So 25 is x, but we got to go find y now, because in our picture we had both an x and a y. So we know this is 25, and that's 25. How am I going to find y?
Plug it in.
Plug it into the box equation, right? The substitution equation is already solved for the other variable, isn't it? Right? So if we plug in 25, we get 200 minus 100 over 3 is, 33 feet and 4 inches, I guess. Right? That make sense?
So your total answer is x equals 25.
X equals 25 and y equals 33 and a third feet, so 33 feet 4 inches. Right? 100, just 100 divided by, all it is just 100 divided by 3, right?
Yeah.
So we could have just said that's 100 thirds feet too, I guess. Okay? Make sense?
Yeah.
Okay? That's optimization. That's it. How much time we got?
10 minutes.
Oh, 10 minutes. We gotta do some more of that.
Trivia. It's been a long week, Mr. Lawyer.
I know. Here, we'll do a quick one. This one is, now I want you guys to tell me why this is actually, it might look harder at first, but this is a way easier problem. Tell me why. No?
You only need a pen. Oh, good guess. Thank you.
this is chemistry today.
Is that Q?
Yeah.
The Q?
Yep. Q sub 0. Q naught.
Mr. Oil, I want to know something funny.
What's that?
I went home. Remember that night we were talking about mini cucumbers?
Yes. You had mini cucumbers.
Yeah, and my mom had a package of mini cucumbers on the counter. And
Did you tell her? Did you optimize?
I
I hope.
didn't,
Okay.
but
Well,
I thought about it.
you should have.
It was funny though. Too many words. This is not.
I know this is a lot of words, isn't it?
5 minutes to write this.
I know. That's why I tried to take a picture.
Well, time to go, Mr. Roy. We got the problem with it now.
There we go. Okay, so this is kind of a cool problem. In an autocatalytic, anytime you have the word auto in something, it means it drives itself. Right, exactly. So in an autocatalytic reaction, the product formed is a catalyst. Now, what's a catalyst? Okay, good. Something that moves a reaction along, speeds up a reaction, right? So if the reaction formed is a catalyst, then that's going to further drive the reaction, right? Okay. So if Q naught is the amount of the original substance and X is the amount of the catalyst formed, the rate of the chemical reaction is given by this. dQ dx, right? So the rate of change of the substance is equal to some constant, K, we don't even know what it is, we don't have to, but it's some constant, times X, which is the amount of the catalyst, times the Q naught minus X, the amount of the substance minus X. Okay. And we can talk about why that is. This really just represents how much has been used up, right? And this represents then how much free catalyst we have. Okay, so for what value of X will the reaction rate be greatest? Okay? So we want to maximize this function actually, don't we?
Yeah.
Right? Does that make sense?
Yeah.
Okay, we're not going to finish this, but at least we'll get a little start on this. So let's call that f of x, how about? Okay, the reaction rate, we're just going to call f of x. Because right now it looks like a derivative, and it is, but that's not the derivative we're going to set equal to 0. We're trying to take that rate and maximize the rate, right? Does that make sense?
Yeah.
Okay? So then we'll just say our function that we're going to deal with, how about we'll call it r for rate. R of x equals kx times q naught minus x, where x is the variable, q naught is the amount of the original substance, right? And x is the catalyst. Okay, what's our domain going to be?
Negative infinity to.
What's the smallest that x could be?
A zero.
It could be 0, and if it's 0, the rate proceeds at what rate?
Zero.
0. So that's probably not our answer, but it could be 0.
Greater than zero.
What's the most it could be? No, it can't be infinity. The most it could be is q naught, because that's the amount of substance, right? That would mean that it's all catalyst, and there's nothing for the catalyst to work on, right? See, the catalyst is causing the substance to break down into, right, something else, which involves creating more X, right, more catalyst. So if there's no catalyst to begin with, you can't start the reaction. But if the whole thing was catalyst, what does the catalyst have to do? Nothing. It's got nothing to change, right? So the upper limit of this is going to be, and it makes sense if you look at this, right? The rate can't be negative, right? And so the biggest, you can see that as X gets bigger, this quantity is gonna get smaller, right? This factor would start to become negative if X got bigger than Q naught.
Yes.
So the upper limit
Gonna include,
is just everything is catalyst. The whole substance is catalyst. Okay. So this is pretty simple then, isn't it? What do we do?
Just find the derivative.
Yeah, we just differentiate. This is really simple. We've got our function, our primary equation in terms of how many variables? One. Just do calculus. It's a really simple one. There's no numbers, that's fine. There don't need to be numbers.
Let's just,
If I want to simplify this by distributing probably, right? So I'll rewrite this as R sub X equals, I can leave the K out front, but K times Q naught X minus X squared, right?
yeah.
I can leave the K out front, it's just a constant, there's no reason to distribute that through. Now if I differentiate, what do I get?
Okay.
I leave my K out front, what am I gonna get, what's that term become?
Q.
Q naught minus
2x.
2x. Okay, would you agree that that's going to equal 0 when 2x equals q,
Yes.
q naught? So x equals q naught over 2, right? That's gonna be our maximum, isn't it? That's the amount that's gonna maximize, because that's the only critical number we got. And we know that at either end of our domain, we're getting 0 reaction rate, right? Either place we go, if I plug in 0 for x or q naught for x, I'm gonna get 0 back, right? So we already know that's gonna be our maximum. We could show it really easily though. If we just take a second derivative, don't we just get negative 2k?
Yeah.
Okay, k is a positive constant, right? So we know that it's negative everywhere, right?
Yeah.
So if we, yeah,
These kind of problems is always gonna be in the exact middle.
no, they won't be. These happen to have both been quadratics, and so they have been, but otherwise they wouldn't necessarily be. So when we make our table then, this is just what it's gonna look like, right? We already know. We got it, right? All that means is horizontal tangent, downward concavity, that's our maximum. So what's the moral of the story? You want to have maximum reaction rate. You start with how much of your substance being a catalyst?
Yes.
Half. Yeah. Okay. Yeah, it is. It's a real life thing. We should real life calculus.